Hey guys, this is Unit 3, Note C. We're going to talk about polarity and shapes of covalent compounds. So polarity is driven by something called electronegativity, which should be something that we've heard of, talked about. Now we're going to look at how it applies to the covalent bonds. If you remember, electronegativity had to do with how negative the atom was when it was in a covalent bond, how greedy it is, how much it's pulling those electrons. So when we look at electronegativity, that's going to describe how much it's attracting electrons in the bond. So if two atoms are sharing electrons, one of them is going to pull harder than the other, kind of keeping those electrons, kind of like a tug of war. There's actually something called the Pauling scale, which will quantify this. So you may remember from your trends that fluorine was the most electronegative atom on the periodic table, and so it has the highest number on the Pauling scale, whereas francium would be the exact opposite, our lowest electronegativity on the periodic table with the lowest number. This is going to allow us to compare things that are not in the same row or same column. But you really should know your periodic trends. You should be able to evaluate two atoms that are in the same row or the same column based on those trends. So just to recap real quick, as you're going across the periodic table, adding more protons, your electronegativity is going to increase. It's going to be better at pulling those electrons. Whereas if you're going down the column, those extra energy levels and that extra shielding is going to make it easier to steal. And so the electronegativity would decrease. All right, so let's look at the different types of bonds this could create. So first of all, it is possible to have a nonpolar bond. Not all bonds are polar. So that would occur in something where you have a bond between two of the same atoms, or two very similar atoms. So like our diatomics. Hydrogen here, for example, would have the exact same number on the Pauling scale. It has the exact same electronegativity, meaning it's pulling evenly on the shared pair of electrons here. So the electrons would be spending equal time in my hydrogen rotations, my hydrogen orbitals, and so one side would not be any more negative than the other. So we would consider that bond completely nonpolar. If there's no polar opposites, it's a nonpolar bond. Polar bonds come from unequal sharing, uneven pulling, where one atom is more electronegative and pulling harder on the electrons. Those electrons will then spend more time in those orbitals of the more electronegative atom. So what happens then is the electron that's pulling harder, that's winning that tug of war, is going to become slightly negative. And there's a symbol for that. This is the lowercase delta sign with the little negative. You may remember capital delta from math class. Lowercase delta, this is the change. This is just a partial change. So then we would have a partial positive on the atoms that are losing the electrons or losing that tug of war. So the atoms will become partially positive or partially negative based on how electronegative they are compared to what they're attached to. So let's look at an example here. Hydrochloric acid, or HCl. So we have a hydrogen Pauling scale 2.20, and on the Pauling scale chlorine is a 3.16. So which one would be more electronegative, the hydrogen or the chlorine? The chlorine, the one that has the larger number, would be more negative. So if I sketch out my Lewis structure here, and yes, we would have the dots around the chlorine, but not the hydrogen, these electrons would be spending much more time in chlorine's area than they would in hydrogen's, which makes the chlorine a more electrostatically negative part of the molecule, and hydrogen then would be like deficit electrons most of the time because the electrons would be over here. So that's going to make it more of a positive part of the molecule. It's not fully positive and negative. There wasn't a complete transfer of electrons as there was with ionic bonding, but it is partially positive, partially negative. So that's going to make the molecule polar. Whenever I have, I should say make the bond polar. In this case, there's only one bond, so yes, molecule 2. I'm going to represent that instead of that chaos of drawing what the electron's doing, just with an arrow. And I would have the head of the arrow showing where the electrons would be going. So the electrons would be headed towards the chlorine. That blue arrow is known as the dipole. So when we draw the positive side of the arrow by the positive side and the head of the arrow by the negative, that represents two poles or dipole. Let's look at a molecule where we would have multiple bonds. So the first thing that you should know about water is it's actually bent. And we're going to get into shapes a lot more in the next section. Trust me on this. The hydrogens are actually bent towards each other instead of laying out linear. And by the way, the reason for that, just to give you a sneak peek into shapes, is because the lone pairs here push the hydrogens away from it. So I'm kind of leading into that because the shape is actually going to help play a role in the polarity, so I want to make sure we have the right shape, but we will go into that more later. All right, so the first thing that I want to look at is what's more electronegative, the hydrogen or the oxygen? The one with the greater number on the Pauling scale would be the more electronegative. So my arrow would be going from the hydrogen into the oxygen for both bonds. So what I've just drawn in blue is the bond polarities. What's most important is the molecule's overall polarity, which is why shape is such an important thing. If I have one kind of bond polarity going to the right and another bond polarity going up, the molecule's polarity would be an average of the two. Think vector addition. It would be going kind of diagonal, mostly focusing on the oxygen. So there would be a very partially negative part of the overall molecule on that oxygen. So in order to determine if the molecule is polar or where its polarity lies, you've got to consider all the bonds and kind of add them up. Picture a ball where the oxygen is. If I pushed it simultaneously to the right and up, where would that ball go? That's kind of what we're drawing with that polarity arrow for the entire molecule, or the net dipole or total dipole. So I lost my eraser. There we go. So there we go. We got our partially negative and partially positive bonds, but then the overall molecule has that partial negative, this total dipole. If you have a total dipole, then the molecule is polar. That is what makes the molecule polar. All right, next I want to look at what polarity has to do with electronegativity and how this difference in electrostatic attraction, or how the different positive and negative strengths affect the strength of the bond. So if you remember when we started this whole chapter, we talked about how the difference in polarity, or the difference in positive and negative, opposites attract, will drive the strength of the bond. So if you had no difference, or relatively no difference, you would have a nonpolar bond, like the hydrogen we discussed earlier. As you start to increase the difference in electronegativity, comparing like the hydrogen to the oxygen like we did before, you could get a polar bond. And the more you increase the difference, the more polar the bond would be. Notice fluorine was the highest electronegativity, and hydrogen is actually one of the lowest you can get of the nonmetals. So you've got a very polar bond there. Right around 2. So you don't have to memorize all these numbers, but this is a good spot to know about. We don't even have a covalent bond anymore. It becomes an ionic bond. So these are then no longer sharing the electrons. A high electronegativity would indicate that the electrons are spending a lot of time with one atom and very little time with the other atom. Once that is a complete transfer, we call that an ionic bond. So in your beginning chemistry classes like this one, we talk about this like it's a black and white thing, but in your more advanced classes, in your AP and your IB, we'll talk about how this is like a sliding scale, a gray scale, having more ionic character or more covalent character. So it really has to do with how different the positive and negative kind of charges or partial charges are in the molecule. All right, so speaking of the molecule as a whole, if the molecule ends up with that total dipole, 2 poles, dipole, you can actually call the molecule itself a dipole. So since hydrochloric acid, or HCl, ended up with this negative charge on the chlorine, we would say that the molecule is a dipole. It is a polar molecule. It is possible, though, to have nonpolar bonds end up as a nonpolar molecule. So carbon dioxide is a perfect example of this. With carbon dioxide, I have 2 double bonds. If you draw the correct Lewis structure, needed, available, shared, you end up with the 2 double bonds and no lone pairs on the carbon. Remember how the water was bent because it had lone pairs on the oxygen? Let me just draw that real quick. It was the lone pairs that caused it to bend. no lone pairs here. So again, we'll get into shapes more later, but I want you to keep in mind that that's kind of driving polar and nonpolar here. So between carbon and oxygen, which one's more electronegative? Well, they're in the same period in the periodic table, so you should be able to compare them. Oxygen has more protons further to the right, and so each bond would have the electrons being drawn towards the oxygen. So if I tried to cancel out, if I tried to add up to the right and to the left, they cancel out 100%. If there was a ball located on the carbon and you pulled on it evenly left and right, that ball would not move. So where would I draw my total dipole? Well, there isn't one. So that makes the molecule non-polar. If there is a total dipole, it's polar. If they cancel out or aren't there in the first place, like with the diatomic molecule, non-polar. The only way to get a polar molecule is to both have polar bonds and have a shape that does not allow them to cancel out. So with carbon dioxide, you would end up with a non-polar molecule. So canceling out to 0. Whereas with water, we also had 2 bonds that were polar, but this time the arrangement, that shape, did not allow them to cancel out. And so we ended up with the polar molecule. There was a net average of the two because they're going in different directions. So you remember this guy where we were able to see that they did not cancel out, and we had that very electronegative oxygen. All right, so that kind of wraps up polarity. There's one more little thing I want to talk about while we're talking about electrons moving around, and that's something called resonance. So resonance occurs whenever you have a double bond that could be in multiple places in an atom. So a good example is our carbonate ion. With carbonate, we have one double bond. Again, if you did needed available shared, you'd realize you need 4 bonds, and so we'd have to put one of those oxygens attached as a double bond. So because of that, I need to pick where to put it. And you may remember I told you it doesn't matter where you put it, because you could flip this around and it would be the same thing. Like if you stood on your head, you're still the same person. But there's something more going on if we're going to talk about resonance. If I actually numbered these oxygens, oxygen 1, this is oxygen 2, this is oxygen 3. If I rotate this, I could keep that double bond on the 1, and that's literally the same molecule, right? But if instead I put it on oxygen 2, now that's actually connected differently, right? And the same thing I could do here, put it on oxygen 3. So what I'm trying to represent here actually isn't spinning the molecule, but that double bond being connected to 3 different oxygens. What really happens is that this double bond, or the extra 2 electrons that are in that double bond, are actually being shared between the oxygen and carbon between oxygen 1 and carbon, between oxygen 2 and carbon, and between oxygen 3 and carbon evenly. This is why we talked about the charge being delocalized or spread out throughout the entire molecule. What's really happening is the structure is an average of these 3 kind of representations. What I'm drawing here is kind of complicated. It's really hard to show a motion in a diagram. So picture this bond rotating between the 3 oxygens. So the way to represent that, to try our best to draw it, is to draw the 3 options and use a double-headed arrow in between the 3 options. One other thing I want to note about the format is even if there's not a charge, you should still put this in brackets or parentheses, preferably brackets, just to kind of separate the 3 separate structures and so that you can put your arrow clearly in between. So you've got to be able to recognize when a molecule has resonance, and that would be whenever you have a possible motion of the double bond, and you've got to be able to draw out the structure so that you can show what the resonance looks like, or at least try to represent what it really is. So that's going to wrap up resonance. The next thing that we're going to look at is the shapes, and that's still part of note C. But I'm going to take a quick break and we'll be right back. Hey guys, we're going to finish up with Unit 3, Notes C, picking up with shapes. So what drives the shape of a molecule is something called VSEPR theory. V for valence, S for shell, E for electron, P for pair, and R for repulsion. So the valence shell, as you know, is the outermost shell. Electron pairs, when we were drawing the Lewis diagrams, we always drew the lone pairs as pairs. And then repulsion. So the most important part of this entire theory is actually the repulsion. Of course, we're dealing with valence shells and the electrons that are in them. We're worried about the repulsion. The repulsion is going to push away the bonded atoms, and so that's going to create different shapes. So it's all about the repulsion. We're going to use a theory to explain how the repulsion drives the shape. Remember, theories explain. All right, so we're used to drawing Lewis structures as two-dimensional. Say I wanted to draw this carbon tetrafluoride, or CH4. I would draw the carbon in the middle and then the H's surrounding it. And if you check your valence electrons, this is the perfect Lewis structure for this CH4. But the real molecule of CH4 would not lie flat on this whiteboard. It would actually have one of the hydrogens coming towards you and one of them going away from you. So how do we draw that? We can have two of them in the plane. So I'll draw two of them with the regular dashes that we're used to. But one of them would have to be coming towards you, which I'll represent with a wedge. And then one of them would have to be going away from you. So I'll trail that off with a dash. So we're going to use a combination of wedges and dashes to show the parts of the molecules that are three-dimensional. Oh. There we go. So I don't usually circle them, but same idea. You want to be able to use the wedges and the dashes to show what's going into the page or going backwards, and then what's coming out of the page and what's laying flat on the page. Usually you can fit the central molecule and then two things in the plane of the paper, and then have one thing coming towards you or one thing going away from you. Sometimes you only need one, either a wedge or a dash. With a molecule that's tetra or four-sided, four attachments, you would need both. So we're going to look at this VSEPR theory, or valence shell electron pair repulsion theory, and see how those electron pairs repel the bonded atoms. So non-bonded pairs are what I keep calling lone pairs. They're the electrons that are not drawn as a line. They're the ones that are drawn as the dots. Remember, they do always come as pairs. The bonded pairs would be each line. So the lines represent the bonds. And as it turns out, non-bonded electrons really hate bonded electrons. So the non-bonded electrons are kind of the culprits behind this VSEPR theory. They're really going to push and push away the bonded pairs. The bonded pairs being, of course, attached to the atom means that atom is going to move. And when we name the shape, we're worried about where the atoms are. All right, so now to go over 5 main shapes. So this is our first of the 5. This is a linear shape. So this would happen with carbon dioxide, where I could have my carbon double bonded to each oxygen. And the oxygens would need lone pairs, but the carbon is full. The carbon being full is really the only thing that matters to the shape. The fact that there are no lone pairs on the carbon means that there is nothing to push the bonded pairs towards each other. So they would lay out flat with a 180-degree angle. So we would call that linear. By the way, even if there's 2 things in an atom, in a molecule, we would still call that linear. Sometimes this gets people stuck. You really got to be careful between linear and bent, but if there's 2 atoms, of course, it's also linear. Oops. Okay. Having some technical issues here. There we go. So the other thing I want to talk about as I go through each shape is how it affects polarity. So when we have this linear line, if both of the attachments are the same, you would either have both arrows going out, or it's also possible to have both arrows going in. But the point is that it is possible for them to cancel. So this could end up being nonpolar. Like we showed with the carbon dioxide, actually has both bond polarity going out, and so the total polarity would be nothing. If you can't draw a total dipole, it's nonpolar. You do have to be careful. I can think of one exception to this. HCN. So this would be the Lewis structure for this hydrocyanic acid. And if you look at H to C, C is more electronegative. C versus N, the N is more electronegative. So if we're going in the same direction, then yes, the molecule is polar. But that's pretty rare. Usually the two attachments are the same, and so they would both be going in or both be going out. So with the linear, you got to watch out for it to be able to cancel. All right, let's look at the other version of a central atom attached to two things. If I have lone pairs on the central atom, then it will bend. So water was an example we've looked at. It is these lone pairs on the water that will cause the hydrogens to kind of close up. The hydrogens would love to be 180 degrees apart, but these lone pairs are big bullies and they're going to push those hydrogens so that they're closer together. So this angle is way less than that 180. It kind of closes it in. It bends it. So we call that bent, or we call it angular, because as you can see, there's an angle that would be formed here. By the way, it's not exactly 90 degrees. It just kind of looks like that on the board. Whenever you have a bent shape, you've got to be careful about the polarity too, because in this case, you would usually be going in two completely opposite directions, in which case you can't cancel. The only exception I can think of to bent being polar is if it's all three atoms that are exactly the same. And of course, if you don't have a polar bond in the first place, you can't end up as a polar molecule. But if you have different atoms involved and you have a bent shape, it will always be polar. Always polar, because you can't have two things canceling that are going in like northwest versus east. Wow. Okay, one's going like north-south, one's going east-west, and that will never cancel. All right, next shape. This is our only shape that has 4 attachments. Tetra actually means 4. You're going to see that in naming as well. So tetrahedral would be a central molecule attached to 4 things. So this would be like our CH4. So we can have our carbon attached to 2 of the hydrogens in the plane, but notice the 3D shape. I could have 3 things line up, but one's going to come towards you and one's going to go away from you. So remember, we use the wedges and the dashes to represent that. We'll have one wedge coming towards you and one dash going away from you. And that's going to allow us to represent the Vesper shape of this CH4, which, by the way, is also named carbon tetrahydride with the 4 hydrogens. And whenever we have the same molecule attached to each one, then those would cancel out. They're actually going evenly out if you think of a 3-dimensional shape, evenly in 4 completely different directions. So that could end up being nonpolar. I will warn you though, if just one of those atoms is different, then although these may all be going in, this polarity would be going towards the chlorine. And so you would end up with a net dipole or a polar molecule. But if they are even, which is more common, then you end up with a nonpolar molecule. All right, so the last 2 shapes that we're going to look at have 3 attachments. It can either be planar or pyramidal. So first, our pyramidal shape. This pyramidal shape will have 1 lone pair. So an example would be NH3. We can have our nitrogen attached to 3 hydrogens. The problem is not all 3 of those hydrogens can fit in the same plane as the nitrogen. Picture this, I know it's kind of moving, but you can pick 3, a plane of 3 of them to get them in there in one plane, but then one of them would either be going towards you or away from you at any given time. So you could use a wedge or you could use a dash. It really doesn't matter because the molecule could be facing you or it could be facing this way. Same molecule, right? So it could be going away from you or towards you, but not all 3 of them can go in the plane. So if you have pyramidal, at least 1 bond has to be a wedge or a dash. You also want to make sure you always complete your octet. So in this case, nitrogen needs another 2 electrons and the hydrogens are already happy. So this would be the way that I would draw the Vesper structure for a pyramidal shape. As far as polarity goes, they're being evenly pulled out away or towards the central atom, But do you see how that central atom is up higher than the other three? Kind of like an actual pyramid, hence the name of the shape. Well, that means that the polarity would either be going up towards the center of the pyramid or all away from the center of the pyramid, which means you're going to have a polarity either going straight down or straight up that's not canceled out by anything else. So this molecule, pyramidal shape, would always have to be polar. There's no way for that up and down polarity to cancel out. All right. So we have two shapes that are always polar, bent and pyramidal. And I say always unless it's like all the same atom. All right, last but not least, we have our trigonal planar shape. So what could allow it to flatten out? Well, we would need a double bond. We need to get rid of those lone pairs. Oops, drew that too close. Trying to make a Y shape here. So if I had a lone pair on the boron, that lone pair would push the fluorines and make a pyramid. So I can't have a lone pair if it's planar, but I have to have an octet. So the only way to get this trigonal planar shape is to have a double bond. So that double bond is going to affect the number of lone pairs on the fluorine. I would need one less because I already have 4, so I need 4 more. And the fluorines that only have a single bond need 6 more. And boron already has the octet. So this would be my structure for BF3. The double bond makes it so that I don't have that extra lone pair. That's going to make it able to be completely flat. All of these 3 attachments can go in the plane because there's not an extra lone pair pushing the fluorines away from it. So this is going to be spread out evenly in 3 directions, which also means that the polarity can actually cancel out. So this could end up being nonpolar as well. And usually they're the same 3 atoms, and so it would be nonpolar. Just like with tetrahedral, though, be careful if one of them is different, that will change the polarity. One last thing I want to point out here. See how that double bond could be on either fluorine? What was that called? That was resonance, where you could have the bond be drawn on the fluorine at the bottom or the fluorine to the left. So we would draw all 3 options, put them in brackets, and put the double-headed arrow in between. That would be the correct way to represent both the VSEPR and the resonance structures for this boron trifluoride. So that's going to wrap up our shapes. Let me just kind of put together a quick little summary here. We have linear versus bent whenever we have 2 atoms attached. So with linear, you would need double bond, whereas bent, single bond, creating lone pairs. You could also have pyramidal versus planar. And you usually say trigonal pyramidal or trigonal planar, indicating it's a triangle, because with some of the extra shapes that you'll learn about in your more advanced classes, there's also square pyramids and square planar. So these are trigonal. With the pyramid, you would have a lone pair on the nitrogen, and with the planar, it would have a double bond, like with the boron trifluoride. Double bond allows it to lay flat, lone pair pushes it. So these are our options if we have 3 atoms attached, like in addition to the central atom. And then there's only one option if you have 4 atoms attached. It is tetrahedral. So tetrahedral would be like the carbon with the 4 hydrogens, where you need both a wedge and a dash. And this is for 4 atoms, including the central atom, or not including the central atom, adding on the central atom plus. So you take your central atom, if you've attached 2 atoms, it could either be linear or bent, whereas the bent has the lone pairs. Pyramidal versus planar, where the pyramidal has the lone pairs. for 3 atoms on your central atom. And then with tetrahedral, you would need 4 atoms on your central atom, and they would spread out evenly. So wherever you have the bending, kind of the pushing away, these are always going to end up polar, whereas the other ones do have an option for them to cancel out if the attachments are all the same atom. I hope this helps, guys. This is the end of notes C for Unit 3. One last set of notes, notes D on intermolecular forces. See you there.